let's consider a simple slab made from glass. So here is our slab, and this slab is kept in an air medium. So we have two media here, we have air and we have glass, and the border between these two media, that is this region, is what we call the interface. This is what we call the interface. At this interface, we fire a ray of light. So here we have a ray of light. So it is hitting the interface at a particular point. And if we drop a normal, a perpendicular line at this point, this is what we call the normal. Now, the ray of light that is hitting this point on the glass can do many things. If this is a very smooth polished surface, even though we are dealing with a transparent material, some portion of this ray will be reflected. So here we have a reflected ray. And if you recall the laws of reflection from earlier classes, you will know that the incidence angle, that is this angle, and the angle of reflection, which is this angle, will be equal to each other. So the incidence angle has a magnitude of I, and the reflection angle will also be the same when measured with respect to the normal. So this is reflection. But what other effects can we talk about here? Well, since this is a transparent medium, a ray of light which is hitting this interface between air and glass will also pass through the medium, but it will show a strange behavior. The reason for this behavior is that the speed of light within air and glass are not the same. And because of this mismatch between their speeds, there is going to be some change in the path of the light. You will notice that instead of traveling straight through the glass, the light is traveling at an angle, something like this. So it is not the same angle at which it entered the glass interface. The question is, how do we calculate this angle? Can we use some kind of relationship to find out what this angle will be? And turns out that there is a relationship which says that for any system containing two media which have different speeds of light, the sine of the incident angle and the ratio of this to the sine of the angle of refraction will be equal to a constant for that particular set of media. And this constant is known as the refractive index. This is the refractive index. It is constant for a given set of two media. The phenomenon by which we see this bending of light as it is traveling from one medium to the other is known as the refraction of light. Now, if this ratio, that is n to 1, by the way, n to 1 is the refractive index of medium 2 with respect to medium 1. If this ratio is greater than 1, which implies that R is less than I, the angle of refraction is less than the angle of incidence, in that case, the ray that is refracting through the interface will bend towards the normal. So, in this particular case, if there was no glass slab, the ray would travel something like this. But instead of that, the ray is bending towards the normal. That is why the angle of refraction, the magnitude of angle R, is less than angle I. On the other hand, if n to 1 is less than 1, which implies that R is greater than I, in that case, the refracted ray will bend away from the normal, and we will see some cases where this is happening, where the refracted ray is bending away from the normal. So this is the basic meaning of refraction. It is the bending of light as it is traveling from one medium to the other. Now, there is a quantity that we call optical density. And what optical density tells us is how fast light will travel in a particular medium. If we say that the optical density of a medium is high, it means that light travels more slowly in it compared to a rarer medium like vacuum or air. For example, diamond is an optically dense medium. The speed of light in a diamond is much less than the speed of light in open air or in a vacuum. On the other hand, air will have less optical density compared to diamond because the speed of light in air is much greater than the speed of light in a diamond. Please note that we should not confuse optical density as a concept with physical density of a material. We cannot predict whether two materials will have the same relationship between their physical densities as their optical densities. These are two separate phenomena, so let's not mix them up together. Now, as I told you that since we are having one interface across which the light is bending, what happens if there are two interfaces? For example, let's again take a glass slab. So here is another glass slab, and we have a ray of light entering the slab at an angle, let's say like this. What behavior can we expect from the slab? So we have two media. We have medium 1. So this is medium 1. We have medium 2, and again we have medium 1. What do we expect to happen? Especially given that the speed of light is greater in medium 1 compared to medium 2. So in this case, let's first drop a normal so that we have a reference to measure the angles. So here is our normal. This is the normal, and we measure the angles with respect to this normal. So here we have the angle of incidence. As we learned before, if the light is entering from a rarer medium to a denser medium, that is n to 1 is greater than 1, in that case, the refracted ray will bend towards the normal. So while the normal path for this ray, if the glass slab would not have been there, would go something like this. In fact, the ray will bend towards the normal. So it will go something like this. So this will be the actual path traced by this beam of light through this material. Now again we face the situation where the ray of light is now leaving a medium for a different medium. So first it was entering from an optically lighter medium into an optically denser medium. At the top interface, at the bottom interface, it is now exiting from a denser medium and entering a lighter medium. So what happens now? Now the reverse will happen. So again we drop a normal. So here is another normal. And here we will apply the rule again. So here we are going from a denser medium to a rarer medium. So in this particular case, the ray of light will bend again away from the normal. So this will be the emergent ray. If you tried the experiment yourself, you would note that the incident ray and the emergent ray are parallel to each other. In other words, since we are dealing with two parallel interfaces, the slab is not bending the light as much as it is shifting the light to a different path. And this shift in the light beam is what we call lateral displacement. There is an easy way to see this happening. Just take a clear glass slab and put it over a newspaper. You will feel as if all the letters in the paper are raised. This is because the image that your eye is seeing of those letters has been laterally displaced, in this case in the upward direction. Now we will discuss the case where the position of an image seems to change because of the refraction phenomenon. For example, let's take a pond filled with water, and there is a tiny little goldfish in this pond. And you are the observer who is observing the fish through the water. Now, normally, if the water was not there, let's take any given point on this fish. Let's take the eye, for example, and a ray of light hits your eye and you are able to see the location of the fish. But now there is a problem. Due to the presence of the water, now there is an interface. We are dealing with an interface. So we are seeing that the light has to travel through not just one medium, but two media. So we are seeing that light is traveling not just through one medium, but through two media. What effect will this cause? What happens here is, due to the fact that this ray coming from the fish is bending at this interface. So if we drop a normal at this interface here and we measure the incidence angle, this is the incidence angle, we notice that as we are going from a denser medium, that is water, to a rarer medium, that is air, the ray of light will bend away from the normal, something like this. As a result of this, the apparent position from where the light seems to be coming will shift, and it will seem to you as if the fish is in a different position than its actual position. The fish will seem to be closer to the surface of the water than where it actually is. And if you see birds which capture fish from the water, they actually have to compensate for the refraction effect so that they can aim their legs or their beaks at the correct position where they can catch the fish. So this is an interesting consequence of the refraction phenomenon in nature. Another phenomenon is the change in the apparent position of the sun in the sky compared to its actual position. Let's analyze this. So here we have the earth. So here we have the earth, and the earth has an atmosphere. So let's say this is our atmosphere, and we have the sun somewhere far away. So here is the sun. As the rays of light travel from the sun towards the earth, if there was no refraction, if there was no atmosphere, the ray would travel straight. But on the other hand, due to the fact that we actually do have an atmosphere, when the ray hits this interface, that is the interface between the atmosphere and vacuum, what we observe is that the light will bend at this interface, and because we are going from a rarer medium, that is the vacuum of space, to a denser medium, that is the Earth's atmosphere, we will actually notice that the ray is bending towards the normal. So the ray will bend towards the normal, as a result of which the position of the sun that we perceive will be different. The sun will actually seem higher in the sky than it really is. In fact, there is a deviation of about 2 degrees between the perceived position of the sun, where we think the sun is in the sky, and the actual position of the sun. So this is yet another consequence of the refraction phenomenon in our daily lives.
Manorama Horizon. Learning made simple.